I hope I am audible. I apologize for missing the last week's session. There was some emergency that I had to attend to, and I requested some postponement of the session, but since NPTEL team was unable to give me, or we both were not able to come to a mutual agreement of the time, so I will see when I can upload the session of week 19 hydrology. But we'll take our this session week 20 session, that is the solid mechanics or strength of materials, whatever you want to call it. I am currently out of station, so we are not going to go through a lot of questions, just 3 previous year questions, and I have to be somewhere at 7 o'clock, so that's why I have started this meeting a little early, because I don't want to get this postponed and again get into conflict with the NPTEL team. So let's start with that. So we have 3 questions. First question is going to be a theory question that is going to discuss relation between the SFD and the bending moment. So when it is minimum, maximum, what is the relation between these two in the curvature and all. Then second question is related to the shear force in a cross section. When you look at it a beam, what is the distribution of shear force, shear stress actually. And the third and last question is going to be uh, getting the BMD more or less for beam which is statically indeterminate. So we have to use a compatibility equation. Alright, so with that, let's start our session. Question 1, GATE 2017, set 1, question number 5. A simply supported beam is subjected to a uniformly distributed load. Which one of the following statement is true? So this question, let me read out the options, but I want to tell you that this question is ambiguous a little bit, right? So because you might see that one of the options in this question here can actually be correct for the given simply supported beam, but in general we don't see that to be correct always. So the answer was given for a general kind of beam, but given the question is asking for simply supported beam, there can be 2 correct answers. So let's start with option A. Maximum or minimum shear force occurs where the curvature is 0. Maximum or minimum bending moment occurs where the shear force is 0. Maximum or minimum bending moment occurs where the curvature is 0. Maximum bending moment and maximum shear force occurs at the same section. So whenever you see in the question that it is maximum or minimum shear force, actually they are talking with the consideration of this sign convention. So if you want to avoid any confusion, just remove this minimum from these options and you just keep it as maximum magnitude. Then it makes a lot more sense. Okay, so let's draw up the question. We have been given a simply supported beam. This is what it looks like, and then we have a uniformly distributed load on top of that. So I'm not going into the detail, but if you draw the shear force diagram, it is going to come out like this. Just a minute. Yeah. So yeah, it is going to come out like this. It is a straight line with 0 in the middle of the beam. One is positive, one is negative. So this sign convention, as you know, for the shear force, it is on the left side if it is up, it is positive. On the right side if it is down, it is positive. So in this case, both the reactions are going to be up and both the supports. So it is going to be positive on one side and negative on the other side. The magnitude is WL by 2, where L is the length of the beam. So you can calculate it if you want. Now this is the shear force diagram. What about the bending moment diagram? So the bending moment diagram is going to look like this. It's going to be symmetric. I apologize if I'm not able to make a symmetric curve here. And it's going to be plus, and it's WL square by 8. Alright, that's the maximum. Now this maximum also occurs at the center, right? So but here we are also talked about, we're also told about this curvature. What is the curvature? So if you remember the formula when we were looking at the stress, at certain distance from the neutral axis of the beam, if you have seen that in your SOM, the formula was something like sigma by y is equal to m by I is equal to E by R. What was this R here? E was definitely the Young's modulus. What was this R here? R was the radius of curvature, right? And 1 by R, also written as K, is the curvature. So looking at this equation, you can see that M is proportional to K. So the bending moment is proportional to the curvature. Okay, let's just keep that in mind. Now, what is the first option? First option is saying maximum bending moment, maximum shear force occurs when the curvature is zero. So maximum shear force that is on the supports occurs when the curvature is zero. So here, if you see here, the bending moment is zero on the supports, and also in the support shear force is maximum. So you can think for this particular case that this is true. But as I said, this question main answer was kept in mind keeping a general beam. So for instance, consider a cantilever beam with a fixed support on one side, and you have some load on this thing. So the shear force diagram will look like something like this. So let's say you have a free load at the free end, point load at the free end P. So this is going to be the shear force diagram, right? And the bending moment diagram is going to be something like this. Now, the shear force is constant and it is not maximum. So, and where it is maximum, not necessarily your bending moment is zero, right? So as I said, this question was ambiguous. In this particular case, this option may seem correct, but it is not always correct. You have to keep that in mind. So we'll just keep a question mark here. Then let's read the second option. Maximum bending moment occurs where the shear force is zero. For this, you need to know one relation. dm by dx is s. What is dm? What is dm by dx? Is the rate of change of your momentum with the distance when you move along from the support. And what is the s? S is nothing but your shear force. So the rate of change of momentum in a beam at any section is equal to your shear force. I'm not writing here in terms of sign convention because we don't need that in this question. What is it saying? Maximum bending moment occurs when the shear force is zero. And what do we know? When M is maximum, dm by dx, that is the derivative of M, is zero, right? That means S is zero. So this option makes sense. Maximum bending moment, when maximum in magnitude, whether minimum or maximum, occurs when the derivative is zero. That means the shear force is zero. So this option makes sense. Right? The second option makes sense, and that is the answer that most of the most of the coaching institutes and most of the solutions have given. But option one is can also be the answer in this case, right? So I want you to know that this question was a little bit ambiguous. Now, what is option C? Maximum bending moment occurs where curvature is zero. That is not the case because they are directly proportional, right? So that cannot be true. Now, maximum bending moment and maximum shear force occur at the same section. That is definitely not true because we just saw that rate of change of this momentum is the shear force. So the function cannot, when any function, any continuous function reaches maxima, its derivative becomes zero. Its derivatives doesn't go maximum. That's just not how the curvature works. So this option also goes wrong. So the correct answer is B in general case, but also A can be the right answer. Right? I apologize, I'm going a little fast here, but you can always watch the videos in the YouTube and rewind and watch it till you get more clarity to this. All right, question number 2. GATE 2007, question number 33. Shear stress at neutral axis in a beam of triangular section with a base of 40 mm and height of 20 mm subject to a shear force of 3 kilonewton is. So we have cross section of the beam something like this. Base is 40 mm and height is 20 mm, and we are asked what is the shear stress at the neutral axis. Now you need to remember this formula, that was tau, the shear stress, is equal to SAY bar by IB dash. What were all these factors? S was the shear force, A was the area of the section where you actually want to get the shear stress. So when we are talking about the neutral axis, we are going to look at this area. Y bar, so area about the neutral axis. Y bar is the CG of the area from neutral axis. B dash is the width of section where you want the stress, and I is nothing but the moment of inertia, MOI, about neutral axis. All right, so these are the things. S is nothing but the shear force. Let me write it for completeness. So do we know some of the things here? Let us see. What is S? S is 3 into 10 power 3 Newton. What is A? A is going to be this area that we have seen here. So for this we need to know this base. Let me call it as B dash because we are going to use that, and this is going to be our small h. All right, so what do we know here? Since this is a regular section, no funny thing is, no C section or nothing is going on here. It seems to be a symmetric section. We can use the normal formula for the CG of the triangle, and that is going to be the neutral axis. So what does that tell us? That tells us that the CG from the top is 2 by 3 h. So 2 by 3 of 20 is equal to h. What that is? 40 by 3. Correct? And from similarity, B dash by h is going to be equal to 40 by 20. So B dash is 2 into h. So 2 into 40 by 30, it is 80, or 40 by 3 is 80 by 3. Correct? So now we know this. Can we calculate our area? 1 by 2 into 80 by 3, that is base, into 40 by 3, that is height. Y bar. Y bar is the distance of the CG of this area from the neutral axis, right? So CG of this area is going to be 1 by 3 of the height from the base. So this distance, that is given as Y bar, is going to be 1 by 3 into h, right? So what is this? It is 40 by 9. All right. Now what is that? D dash again, we just calculated 80 by 3. And I, yes, I is going to be the MOI of this triangle about the neutral axis. So if you watch my previous video, I have told you a trick of how not to remember the moment of inertia for this thing for the triangle, and how you can back calculate it if you just know BD cube by 12 as in case of the rectangle. But here I'm just going to write the formula. So we have BHQ by 36 as the moment of inertia for the triangle. B is nothing but 40, H is nothing but 20, Q by 36, that is the moment of inertia. So when you substitute all these values into this formula, you are going to get 3 into 10 power 3 into area, that is 40 by 3 whole square. So if you just simplify this, into y bar, that is 40 by 9 divided by I, that is 40 into 20 cube by 36, and into b dash, that is 80 by 3. So upon simplification, you will see that the value of tau that you are getting is 10 Newton per mm square. And I have also told earlier, this Newton per mm square is nothing but megapascal. So 10 megapascal is the answer for this question. All right. So this was just a formula based question, just to jog you up and make you aware that these formulas are important. Now this next question is a little bit conceptual, and we'll see how to solve this. So GATE 2015 set 2, question number 15. A horizontal beam ABC is loaded as shown in the figure below. The distance of the point of contraflexure from end A is. Now what is this point of contraflexure? Point of contraflexure is when the bending moment of the beam becomes 0. We just have to find out what is the bending moment, what is the location, what is the value of x when the bending moment becomes 0. Now we can see easily that this beam has the degree of static indeterminacy 1. So we need one compatibility equation to find the reactions, all the reactions, right? So how do we do that? You might remember a question where we had to find out this kind of reaction, right? This is a standard question that we are asked. How did we solve this question? We separate this beam into two, one like this and one like this, right? And when we calculate the deflection due to this point load at this free end, and then we put this reaction as R and calculate the deflection due to this point load at this free end, and then equate them so that their net deflection at this support becomes 0, and it's a simple it becomes a simple question, and we get the value of R. But in this case, the trick is the load is beyond the support, right? When you had this kind of question and you wanted to get the deflection at this point, let me keep this as A and this total beam length as L. What was the deflection? Deflection was PAQ by 3EI. Deflection was PAQ by 3EI plus PA square by 2EI into L minus A. This was the deflection. But this is to extrapolate, because it was the curvature of the beam looks something like this till the load is applied, not linear, and after the point of load application it becomes linear. So we just multiply with the slope, what is the value of this distance, and we added this part to this main deflection. So that was an easy question, but in this question we cannot use this formula because we have to identify the deflection at a point that is ahead of this beam. So what we are going to do, we are going to break this beam. So if you look at this given load, what do you see? That this point is being applied with a 10 kilonewton force downwards, and also a moment, right? What is the moment? Moment is nothing but 10 into whatever this distance is. So for instance, forget that there is a support there. Simply support, just put it as R here, and this has 10 kilonewton force here. We shifted it, but when we shift it and you remove this section, you have to also carry forward that moment into this section. So that will be 10 into this distance is going to be 1 minus 0.75, 0.25 meters. So it is 2.5 kilonewton meters. This is the moment. So let me just write this here. Right, so this is the moment that you are going to apply here. Now we can easily apply that compatibility equation and we can get the value of R. Why do we even need the value of R, you may ask? Because when we want to calculate the moment at any section, we need to know all the reaction forces at this beam, or at least whichever is most convenient. You can try to get this reaction at A and then moment at A also, but I would not advise that, because then you need to perform or calculate two variables, and then you need to calculate the moment at each section. That becomes a lengthy portion. But if you approach this problem, uh, if you approach this problem like this, it becomes a very simple problem. Now, what do we need to remember? We need to remember three things, or maybe you can say two things. Yeah, only two things. What we need to remember: what is the deflection at the free end when the load is applied at the free end? It is PLQ divided by 3EI. And also we need to remember what is the deflection at the free end when a moment is applied at the free end. That is PL square divided by 2EI. If you know these two things, then this question is uh, not tricky. So let's now write the steps here. So we have the load, unit load from the top is 10 kilonewton. That is going to uh, put this beam downwards or move this point downwards, and then we have the 2.5 kilonewton momentum that is also going to pull this beam downwards. So then we can write 10 into this length, that is 0.75, 0.75 cube divided by 3 EI, plus the momentum 2.5 into 0.75 square divided by 2 EI. This downward movement from these two forces is going to be equal to the upward movement from this alone reaction itself. It's going to be R into 0.75 cube divided by 3 EI. Now when you solve this, and I hope you too, when you are watching this video, you are going to get the value of this reaction as a nice whole number of 15 kilonewton. Okay, so this is going to be the value of this reaction force, that is R. That makes this problem very, very simple. This is your reaction force. I'm just removing the diagram of the support, and this is the load that you are given with originally. This is 0.75, this is 0.25. All right, now what was the original question? See, we had to do so many things just because these people decided to shift this load beyond the support. If it was here somewhere, it was a very short question. But just because they moved this load a little bit further, this question became much more conceptual and much more interesting. Okay, now what was the original question? Sorry, I got deviated. This question is the distance of the point of contraflexure from the end A. What did I say? The point of contraflexure is the point where the bending moment is zero. Now you look at this. Do you think the bending moment is going to be zero at this point in any case? No, right? Because why? When you are calculating the bending moment at any section, that is x distance from here, you are going to ignore this highlighted area, the whatever I have highlighted. You are going to ignore the highlighted area beyond this point, and you can easily see that the bending moment is going to be 10 into x, right? So it is, and whenever actually when they ask this point of contraflexure, it means that they are not actually talking about this free end. So you should not, write the answer as 1 meter, because that is here also the bending moment is going to be zero. They are somewhere in the middle. The bending moment is going to come zero. So that's what we have to find out. So we know that it is not going to be between these two loads, because only one load is actually going to create the bending moment here, right? So how do we know where it is going to be? It is going to be beyond the 15 kilonewton. So now let me write here x. Here somewhere the bending moment is going to be zero, because this is creating a clockwise momentum and this is creating an anti-clockwise momentum. So they are going to cancel out each other. So now let's compute 10 into x. 10x is equal to 15 into x minus 0.25. So 10x is equal to 15x minus 15 into 0.25. X value that you are going to get is 0.75 meters. So from the free end, x value is 0.75. The bending moment is 0 at 0.75 meters from the free end. But the question again, the trick, this is a cheap shot actually, because most of the people would have got this question wrong only because they were in hurry and didn't read that they're asking from the end A. So even if you did all these things correct and you just put the x value as 0.75, you would, and I apologize, I think I lost the internet. Okay, came back. I hope, yeah, it came back. So even if you did everything correct and you forget to calculate the distance from here, you would have lost 1 mark here. So the answer is going to be 1 minus 0.75, that is 0.25 meters. This is the distance where the bending moment is 0, and that is the point of contraflexure. So 0.25 meter is the answer. All right, so what have we discussed today? We have discussed 3 questions. As I said earlier, first question was related to the theory of the shear force and bending moment. Second question was with calculating the shear force at a cross section in a beam, which was basically a formula based question, just for revision of this formula. And the third question was a little bit tricky question, where we have seen how to use, how to use the superimposition in a different way than we are told. All right, so I'm going to end this session now here. So as I said in the earlier, I have to be somewhere, and I didn't want to postpone this session like last time, because I have told this because the NPTEL team is not able to give me a dedicated time to take the week 19 session. So I'm going to take that session some other time, but so this that's why I had to start this session early. I'll try to upload this recording by the end of today. Even though I am out of station, I don't know whether the data will be sufficient or not. But yeah, I'll try, and you can check the video in the YouTube channel. All right. Thanks. And oh, okay. Yeah, please tell me, please. Oh, okay, okay. Thank you, thank you. All right.